Hello and welcome to another DIY Engineers video. In this video I'll be going over the MPU 6050 module, which has a 3-axis accelerometer and a 3-axis gyroscope all in one, meaning it can measure accelerations on the X, Y, and Z axis and also measure rotational velocity along those same axes. In the video we'll be covering the sensor pins and directions, how to connect it to the Arduino Uno, programming in Arduino, testing in Arduino, and even doing a 3D modeling simulation to show what the sensor is reading as you move it. So if you're interested, please join us for the rest of the video. Let's get started. So now let's talk about the MPU 6050 module and the main parameters. It has an accelerometer range that can go from plus or minus 2G to plus or minus 4G, or you can also run it in plus or minus 8G or 16G. Or of course, G is a gravitational constant, which is 9.81 meters per second squared. For the gyroscope, which is also built into the module, you can have it at plus or minus 250 degrees per second, plus or minus 500, 1000, or 2000. All of them in degrees per second. It has an input voltage of 3.3 volts all the way to 5 volts, which means you can feed it with your Arduino Uno. So now, what are our pins? It has 8 pins. We have VCC, where we provide the power input, ground for the ground, which connects to your Arduino ground. Then we have SCL and SDA for the I2C clock pin and your data pin. And you also have XDA and XCL for external I2C pins for data and clock. You have a pin called ADO, which allows you to change the I2C address of the module in case you're running other things on I2C. And then you have an interrupt pin, which allows it to wake up whenever there's any action or sensing going on. You can also see in the actual board, so you can see here, there's a Y and an X axis shown by the right hand rule. Then you know that Z will be up, as I've shown here on this axis shown. And then you have roll and pitch and yaw relative to those axes. Here's how you would connect it to the Arduino Uno. We actually, in this example are only showing 5 inputs connected because we're not using the external I2C pins, or we're not changing the I2C address. So we first have VCC connected to 5 volts on the Arduino Uno. We have ground connected to ground. SCL is connected to the SCL pin, and SDA is connected to the SDA pin. And then we have the interrupt, which we're connecting to digital input output number 2 on the Arduino Uno. So now the next step is to go ahead, open Arduino, and let's install the required library. To do that, you go to Sketch, Include Library, and then click on Manage Libraries. You then want to go ahead to the search bar and type MPU 6050. The one you're interested in is this one, which I already have installed. All you would have to do is select and click Install. I won't do it since I already have it. So once you do, the next thing you want to do is go to File, Example, and go to MPU 6050 and click on MPU 6050 DMP6. And this will open the main example that we're going to be using for this. So to start using this example from the library, all we have to do is scroll down to the section where we define what outputs we want. So in here we have the quaternions, we have the Euler angles, yaw, roll, pitch, which is turned on by default. We have real acceleration, world acceleration, and the teapot, which is for 3D visualization. In this case, we have yaw, pitch, roll already turned on. All we're going to do is uncomment this one so that we can get the real acceleration. And if you read it, the lines or the comments above says, to uncomment that, if you want the acceleration with gravity removed, this will be acceleration within the reference frame, basically, of the accelerometer. So X plus will always be X plus regardless of the way this sensor is looking at, which means that we're recording and outputting the acceleration from the sensor's frame of reference. If you want something different, then take a look at output readable world acceleration, which basically will adjust the output such that the frame of reference is relative to the world and not relative to the sensor. So with that, we can go ahead and send this code to the Arduino so we can test the sensor. So let's go ahead and press upload. Now that we're done uploading, we can go ahead and open the serial monitor. And you're required to enter the input here and then press enter. So for a second, I'm just going to stop the auto scroll so you can see this is essentially giving you the acceleration, and then this is the yaw, roll, pitch angle. The angle is presented in degrees relative to the original orientation, so anything you see here can be minor noise. And this is actually supposed to be a value that can go from negative 32,750 to positive 32,750, where that is just the numeric value, and how much sensitivity just depends if you pick the option for 2G, 4G, 8G, or 16G that we talked about earlier, or 1G equals 9.81 meters per second square or 32.19 feet per second square. The default setting for acceleration is 2G. Basically, this means barely no acceleration. Now, I'll go ahead and turn on the auto scroll again. We can go to the bottom, and you can see that if I change now the orientation, we're seeing some accelerations as I move it, and also some different angles. So now let's go ahead and change the code to perform some 3D model visualization using Processing IDE. All we gotta do is go to the same section that we edited before. We will comment the line that we had been using before to get the yaw, roll, pitch, angle, and degrees. Same thing for acceleration. And we uncomment this one that says output teapot. So with that, just go ahead and upload the code. Okay, so now we're ready from the Arduino standpoint. All we have to do now is install Processing IDE, place the right code on Processing IDE, and run it so we can visualize the orientation of our sensor. Now, I left a link in the description to take you to the Processing IDE download page. Click it, and once you get there, make sure to click the link to the operating system that you own. For me, it'll be Windows 64-bit, which I will click to start my download. Once fully downloaded, go ahead and click to extract all the files. This will take some time. So now open the folder and double click on Processing IDE to start the program. Then all you gotta do is start to import the required library. So go to Sketch, Import, and Import Library, which will open the Contributions Manager. In there, you need to type Toxic and then pick the Toxic libs to install the Toxic library. Once you click Install, it will start downloading, and then it will start installing. Shown on fast forward so you don't have to wait forever for it to install. Once complete install, it will show as installed, and then on the top row where it says status, eventually you will see a green check mark showing fully installed. So now that you have all required libraries for Processing IDE, you have to open the required file to run the 3D visualization. So go to File, Open, and you need to go to the right location of the Arduino folder that contains the library for MPU 6050 and find this file. So you can see here that for me is on my PC, then Documents, Arduino, and then from there on, once you get to your main Arduino file, is libraries MPU 6050, examples, MPU 6050 DMP6, processing, MPU teapot, and then you select this file. This is it, and once you get here, all you have to do is then click Run. Will take a little bit, and then it will show a window with the 3D model. Alright, so now you can see the output of Processing IDE and a video of me moving the accelerometer through a 3D printed part that looks like an airplane. So you can see that as I move it in space, Processing IDE mimics the shape and the orientation of such shape in space. I move it up and down or sideways, and it also goes along with it. So you can see that the MPU 6050 is processing the angles pretty well and keeping up with it through the integration of the gyroscope and accelerometer to keep, track of motion. So I hope you guys enjoyed this. If you did, please consider subscribing and giving us a thumbs up. Thank you very much, and see you in the next one. Bye.
Failure to try to innovate at all comes with a big penalty. You'll be fired. If somebody doesn't even try to innovate, or their innovation aspirations are not very good, then yeah, they will no longer be at the company.
Elon Musk, the CEO of Tesla, sent an email to everybody at his electric car company late Tuesday requesting that Tesla office staff return to in-person work or leave the company. Anyone who wishes to do remote work must be in the office for a minimum, and I mean minimum, of 40 hours per week or depart Tesla. This is less than we ask of factory workers, Elon Musk said in an email headlined, "To be super clear," adding that the office must be the principal workplace where they contact other workers daily, not a remote branch office unrelated to the job duties. Employees at various firms have revolted over the return to office regulations and long commutes as a result of their use of working from home or hybrid practices. However, Elon Musk followed up with a message to everyone confirming the company's stance. He indicated he would personally consider any request for an exception to the policy, but he also said that if you don't show up, we will assume you have resigned in most cases. Early Wednesday, someone asked, "Hey Elon, any additional comment to people who think coming into work is an antiquated concept?" And he responded that they should pretend to work somewhere else. The policy is opposed to that of Twitter that Elon Musk is looking to acquire, which has previously stated that workers can work from home forever if they so desire. Wherever you feel most productive and creative is where you will work from home full-time forever, Twitter CEO said in a statement to the company's almost 100,000 employees in March. Just before Elon Musk's interest in purchasing the social media network was revealed. Unfortunately, that will not be the case with Tesla. Elon Musk said it's especially crucial for senior executives to be seen in the office, which is one of the reasons he virtually resided at the Tesla factory in Fremont, California during the company's production struggles in 2017 and 2018. "If I had not done that, Tesla would long ago have gone bankrupt," he said. "There are of course companies that don't require this, but when was the last time they shipped a great new product? It's been a while." In addition to that, he said that Tesla has and will create and actually manufacture the most exciting and meaningful products of any company on Earth. This will not happen by phoning it in. According to the New York Times, Elon Musk apparently wrote a similar email to the staff at SpaceX. Elon Musk had previously sent an email to Tesla executives stating that they must work in a main Tesla office, not a remote branch office unrelated to job duties. For example, being responsible for Fremont factory human relations but having your office in another state. Elon Musk has recently praised Tesla China staff in Shanghai for burning the 3 a.m. oil while Americans want to avoid going to work at all. For months there, thousands of Tesla employees have been efficiently locked in working 12-hour shifts 6 days a week. Many people slept on the factory floor until recently as part of a closed-loop system to keep the coronavirus out and automobiles running off the assembly line. Workers are being shuttled between the facility and sleeping accommodations, either old factories or an old military camp, with day and night shift workers sharing beds in makeshift dorms. It's not the first time Elon Musk has been criticized for his tough love treatment of staff. Keith Rabois, a Silicon Valley venture financer and entrepreneur, tweeted a tale about his friend's management style about 2 weeks before Elon Musk agreed to buy Twitter for $44 billion. He said that Elon Musk, while standing in line for a coffee at SpaceX, saw a group of interns wandering around. According to Rabois, Elon Musk threatened to fire them all if it happened again, and security cameras were installed to check compliance. On this note, according to surveys, the majority of office workers prefer to work at home. Many companies outside of Twitter have declared more flexibility for employees who want to work remotely since reopening offices following the COVID-19 shutdowns, partially as a tactic to maintain or attract talent in a very tight labor market. However, the world's wealthiest person appears unconcerned about this dynamic. If Tesla and SpaceX employees do not comply with Elon Musk's demands, they may soon be out of a job unless the billionaire changes his mind, which we doubt will happen. I have crazier Elon Musk news that I just found. Click the video on the screen to watch.
This picture is about the transistor. There are 3 transistors here in this collection of small electronic parts. The original point contact type, the junction type, and the phototransistor. And here is a more complex type of transistor. This is called the junction tetrode. These tiny transistors are destined to play a big part in our electronic age. They will make possible smaller, more compact electronic devices that will need less maintenance and have a longer life. But to grasp fully the importance of these new members of the electronic family, let's recall the wonders made possible by the high vacuum tube, the common radio tube. The roots of the electronic age reach back into the early years of our century. In 1907, Dr. Lee DeForest discovered that a grid of fine wire placed between a filament and a metal plate in a vacuum tube could control the flow of electrons between the filament and plate, and the tube could be made to amplify as well as detect electrical waves. He called this amplifying tube an audion. Weak signals applied to the input or grid of the audion caused similar and much stronger signals to flow from the plate or output. A few years later, 2 scientists, Dr. Arnold of Bell Telephone Laboratories and Dr. Langmuir of General Electric, working independently, found that by pumping out the audion tube to create a very high vacuum, they obtained greater fidelity and stability. Here is one of the first high vacuum tubes that started us on the way to the wonders of our electronic age. By 1915, telephone research physicists and engineers had succeeded in developing methods of manufacturing the vacuum tube with sufficiently uniform characteristics so that hundreds of them were installed as amplifiers, thus making possible the first telephone line between New York and San Francisco. And 3,000-mile transcontinental telephone calls became a reality. This same year, 1915, at Arlington, Virginia, telephone engineers hooked together 500 vacuum tubes to generate enough radio power to send the human voice across the Atlantic for the first time in history. Words spoken into a radio telephone transmitter at Arlington were heard by engineers listening at the Eiffel Tower in Paris and also at Pearl Harbor, Hawaii. 1920 brought the beginning of radio broadcasting, but a vacuum tube radio receiver was a real luxury. Then, the next 10 years gave us talking motion pictures, transoceanic radio telephone service, television demonstrations, and ship-to-shore telephony. With our electronic age in full swing, the coaxial cable, the cathode ray tube, the iconoscope, and the image orthicon, aided by hundreds of more conventional vacuum tubes, gave us television, radar for war, radar for peace, and then microwave radio relay to speed hundreds of telephone calls as well as television programs from coast to coast. The heart of all these electronic systems has been the vacuum tube. But the Bell Telephone Laboratories have added an entirely new and different heart to modern communication systems, the transistor, operating on a new and different principle arising from basic research on solid substances and how the electrons inside them behave. How did it all come about? Well, doctors Shockley, Bardeen, and Bratton and their associates at the Bell Telephone Laboratories were working on a problem in pure research, investigating the surface properties of germanium, a substance known to be a semiconductor of electricity. Their study suggested a way to amplify an electric current within a solid, without a vacuum or a heating element. And after months of calculations, experiments, tests, the transistor was born. The transistor, a new name, a new device that can do many of the jobs done by the vacuum tube and many the tube can't do. Let's see how the transistor and tube measure up. First off, the vacuum tube is power hungry. While a tube like this generally demands a watt or more of electricity, a millionth of a watt is enough for the transistor. Even a makeshift battery of moist blotting paper wrapped around a coin can power a transistor. The vacuum tube gets pretty hot, sometimes a little too hot. That's why in complex devices, the tubes must be spaced far enough apart for proper ventilation. Since transistors remain cool, they can be crowded together in a small space. In size, reliability, and ruggedness too, the tiny transistor has many advantages. And research goes on to make it still more useful. Many new and improved types of transistors have followed the early models, but transistors are no longer just an experiment. Here, they are being produced at the Allentown, Pennsylvania plant of Western Electric, the manufacturing and supply unit of the Bell system. Different types for different purposes. The Bell telephone people have lots of jobs lined up for them. Jobs based on the transistor's ability to amplify speech sounds in this way. This is how my voice would sound over a 75-mile telephone line that has no amplifying device. Now, with a transistor amplifier in the line, my voice is amplified so that you can hear me distinctly. This, for example, will mean that in isolated farmhouses, far from central exchanges, the transistor, right in the telephone, will make it easier for the farmer to hear and be heard on his rural telephone. And transistors can replace many of the vacuum tubes used in providing long-distance telephone service. Because they are so tiny, transistors have made it possible to miniaturize many types of electronic equipment. This equipment requires less space and will cost less to maintain. Transistors may also be used in multi-channel telephony, which increases the number of calls that can be carried at the same time along telephone lines. When you dial direct from your town to a distant city, transistors in this route selector may be helping to